Hello? Okay. Ohayo gozaimasu. I speak only 5 words of Japanese, so please forgive the English. But yeah, my name is Hamza Rauf. I'm an engineer on the support team at OPAL-RT Montreal. I've been in Japan for the past couple months, providing support directly to some of our clients in Japan. So it's nice to see some faces that I've seen on Microsoft Teams. Now I get to see the faces in person, which is a good change. And so, yeah. Use this? Okay. Thank you, Takiya-san. And so, yeah, today I'll be demonstrating 2 demos, and they're going to build upon the concepts that Yutaka-san has introduced. Because the 2 demos, the first is PS101, in which I show off the smart inverter library with the OPAL-RT simulator. And then second is the eHSGEN5 onboard charger demo, which shows off the capability of our simulators to perform these very detailed and difficult simulations for a lot of these electric vehicle dynamics and models. So we're going to start with PS101, and then we'll go through it, and then we'll swap over to the onboard charger demo afterwards. Okay. So first and foremost, now the text is tiny. Pierre-Francois Allaire is correct. So first and foremost, as we're all well aware, renewable energy is becoming an increasingly important phenomena that we have to account for in our grids. So there are many, many, many challenges with renewable energy integration, as I'm sure some of you are aware, namely just even understanding what is going on inside your grid and how those dynamics interact with each other. And most notably, obviously PV and solar, wind turbines, and battery energy storage systems are in particular quite prominent. So what are the challenges that come with this? So in the North American context, one thing I want to highlight is that we have established codes that have been put up by our utilities and regulators such as NERC. And so these newer revisions of newer codes require more complex and more detailed simulation for your control and for your components. And so in the North American context, we have these new codes that we must abide by and follow. Now, how do we at OPAL-RT help support our manufacturers, help support our clients so that they can design their own controllers, they can design their own models to comply with these new codes and new difficulties that arise? One way that we are doing that is by collaborating. This is just a quick little diagram showing all the different levels of control that these codes affect. So there's primary level, there's secondary level, tertiary, and so on and so forth. So there's lots of different levels of control to consider. And at OPAL-RT, we've developed, in collaboration with CanMet, as Yutaka-san had introduced, we've developed the Smart Inverter Toolbox. So CanMet is essentially just a research institution in Canada, and they have various offices across some of our provinces. The picture you see there on the right-hand side is actually their Quebec office in Varennes, and we work quite closely with them, and we often go to their office to help work together on our simulations. So in collaboration with CanMet, we have developed this Smart Inverter Toolbox to help address these challenges and these new codes that have arisen. And so you can see on the screenshot on the left, there are basically a diagram of all the components that we have in terms of protection and control. So for now, I'm going to focus on the primary and secondary level of control, namely how we can make it so that our renewable energy, that it's properly working in grid following mode, providing PQ support, PV voltage, PV as well. So these are the things that I'm going to focus on, and these are what are going to be demonstrated in this demo. So now as to the model itself, this is a model that we've adapted from an NREL model, actually, the National Renewable Energy Laboratories in the United States. It's a model in which you have three basic battery energy storage systems, and then also some wind and solar. All these IBR resources, inverter-based resources, they are supplying a load. Also, this microgrid area is connected to a larger grid network. Now, at that point of connection between the grid and the microgrid, we have implemented a real hardware relay. You can see it on the table over there when we go look at it. And so we want to demonstrate how using this demo and using this real hardware, we can test and validate that our real hardware is properly performing the functions that it should as according to the codes that have been recently implemented. So in this demo, the key thing the relay does is it ensures synchronization between the microgrid and grid. Obviously, when the microgrid is by itself, it's not connected, it's running at its own phase, its own frequency, its own voltage levels. So when you connect it to the grid, there's the big challenge of how do I synchronize these two? It's quite difficult. There's a lot of control involved. And so in this demo, what we're going to demonstrate is when I close that grid connection, you'll see that the relay, it will basically be in charge of the closing such that it is synchronized closing. And then it also will provide and control the PV to provide the appropriate support so that it gets to a nice even level on both sides. And that's the goal of this demo. Now, these are, apologies for that. Now, these are two screenshots before and after synchronization. I'll also play the video so you guys will actually get to see the video. But on the left-hand side, you can see that the green little square or the breaker, it's presently open, like it's not connected. The two areas are separate, okay? And correspondingly, you can see on the bottom of the screenshot, there is the relay display, the LED. It may be a bit tiny, apologies for that, but we'll see it in the video more clearly. You can see that on the bottom left, that there is almost a 180-degree difference between both on either side of the breaker. And so this is a big phase difference because they're almost 180 degrees far. They're opposite pretty much. So after the relay, after the command is sent to connect to the grid, you will see that the breaker turns red to indicate a closed connection. And then after that closed connection, you see that all of a sudden that basically the angle goes to 0 degrees because both are synchronized to the grid effectively. So I want to emphasize that 180 degree or 100 degree, I forget exactly the number, on the left-hand side, that shows the difference between the microgrid and the grid. And then afterwards, when both are synced, you'll see that it becomes 0 degrees basically. And so now I'm going to play the video to demonstrate this. Now, well, to show off a demonstration that I did last week. And just going to go to the PowerPoint. And then PS101. Yep. Yep. Yeah. Okay. You have to. Apologies. One moment. Okay. So just very briefly, these are the two pieces of hardware. There's the OP8707XG on the left, and then there's the SEL relay. Now, on the relay LED screen, you can see various measurements and just the general status. The connection between the two is quite simple. The OP8707XG is sending analog measurements to the relay. So the relay is getting measurements from the simulator of namely voltage and current. Then there's also just a central Ethernet router to connect all the devices. Now, speeding forward a little bit in the demo, because it's just a hardware tour, it's nothing too special. It's just showing the connections at the back. It's quite simple. I want to now go to the actual simulation. All right. Okay. Now, 1 moment. Okay, so just to explain the dashboard screen really quickly, on the bottom, we have the controls of, namely, how much load is being implemented. So we can adjust the load profile, and we can then see the corresponding adjustment in our PV and also battery energy storage systems, and you'll see them immediately go in to compensate for it. Then also on the third slider, we actually have the amount of PV. So for example, if we have, say, a cloudy day, we can reduce the amount of PV power. Now on the buttons, we have just various modes. So the bottom 3 buttons can disconnect or connect the breakers for the battery energy storage systems. So for example, say one of the battery buses is offline, you can disconnect it. But the main thing I want to highlight is actually that activating that grid connection. It's presently off right now, but later on in the video, we activate it and you see the corresponding change with the relay angle. Now I'm just going to continue it really quickly. It is a long video, so I'm going to skip through various parts of it. But in the beginning, I just simply show the overall diagram. And then I want to then go next to this. At this point, okay, so this is the point of emphasis. I'm about to connect my microgrid to my grid, and you see that on the bottom left-hand side, the relay will pop up. Now, the front screen of the relay, and it will show the angle of the angle difference between both sides. So right now it's about 156 degrees. Now I'm going to send the command to connect to the grid. And then once I send that command, the relay will be in charge of making sure that the close happens at the appropriate moment. So after the close is done, you see that the angle is basically 0 degrees. Both the grid and microgrid are at the same phase effectively. And that's the big task here, and that was one of the big challenges that we seek to address with this smart inverter toolbox. Effectively, we developed these controls, all these new components, so that making this sort of testing is easier and more doable for all of our clients. So yeah, that's about it for this PS101 demo. I'm now going to switch over to AU102, which focuses on our automotive applications. Close and then there we go. So this is AU102. Now, the goal of AU102, once again, is to show off our basically application specialties for automotive applications, and in particular EVs. As we all know, EVs are also becoming more popular, just like renewable energy. And we seek to help our clients model, test, and examine those sorts of applications. So one of the big and difficult problems with EVs is that besides it being a new technology, it's a very new technology and it's very complicated. To accurately represent all the complex interactions that happen inside an EV is quite difficult. Because, for example, we have like a motor, of course, but then we also have an inverter and also an onboard charger, and alongside a battery pack. So there are different levels of detail required for our accurate simulation. And so we need to use both the CPU and also like at the microsecond level, but then also we need to leverage an FPGA to get to those nanosecond levels. Because once we get to these onboard chargers, these inverters, they're switching very, very, very fast. And we require the use of an FPGA to accurately represent that sort of phenomenon. So the way we are seeking to address this is one of the big breakthroughs. We released it a few years ago, but we've made it such a mature technology now. It's eHSGEN5. eHSGEN5 is a big, big boost to our capabilities to model very fast, high-frequency dynamics comfortably on the FPGA. And in this demo, what I will do is I will show you the circuits that we have modeled in eHSGEN5. For those of you who are already familiar with EHS, it'll look largely the same, but under the hood, the EHS solver has been very greatly improved, and it allows us to do these high-frequency simulations. So in essence, we are going to show off both an FPGA simulating these complex fast-switching dynamics, and also using the CPU to simulate more of the slower dynamics, namely just it's basically some of the battery stuff, effectively, because the battery here is modeled in the CPU, whereas the actual inverters and onboard chargers inside the FPGA. So just in a snapshot, there are 4 parts that we are modeling. We have the battery pack, we have the motor, we have the inverter's motor, and then we also have the onboard charger. Now, the onboard charger is the one that uses an LLC topology alongside a boost power factor converter, and whereas the motor is just simply a PMSM with just a standard 2-level bridge. Now, so we have all this modeled on our OPAL-RT simulator, but how do we generate these switches? How do we control the firing of these gates such that we get good power delivery to our motor and also whenever we need to charge our battery? That is handled by the OP8666, or our microcontroller in this case. So the microcontroller here just simply seeks to measure what is going on inside of our simulation and then generate the appropriate switching gating signals so that we fire and we control these fast switching components as effectively as possible. So just a brief bit about the actual topologies. The OBC, or onboard charger, is a cascaded topology. It's a boost power factor converter followed by an LLC. The LLC is switching at roughly at 200 kilohertz, and the gating signals that control the LLC are being sent from the OP866. So this is one of the big differences with eHSGEN5. We can simulate these really high frequency switching dynamics accurately. And as you can see, I've included a screenshot from our schematic editor showing what the topology actually is. Now for our motor, it's, as I said, it's simply a PMSM with an inverter. Once again, the switching here is also handled by the OP866. And in particular, the way this demo will play out is, first, we are going to use the LLC topology to charge our battery. Just going back one slide. Basically, the terminal of the LLC at the very end has a resistor. That resistor effectively represents our battery, okay? So once we start our demo, we're going to charge up our battery to a sufficient level before we activate our motor. We need to ensure that our battery has at least an 80% state of charge, or SOC, before we can really begin running our motor. Once we do part 1 of the demo there and we get the battery to a sufficient level, the next step after that is to activate the motor, in which we send a speed command, and then the motor begins spinning, and we get those we get the inverter for the motor firing. So yeah, after our battery is sufficiently charged, we then activate the motor and then observe all the currents delivered, and then look at the beauty effectively of the EV. So the entire time, by the way, the OP866 is monitoring what is going on and the states of inside our simulation. So the OP866 is namely doing DQ current control, and it is then generating PWMs to send to the actual simulator. Now, the measurements of interest are the speed of the motor. So the OP8666 checks the speed and with respect to the speed reference, and also the currents and theta or angle of our motor. So using these measurements, it transforms these into the DQ reference frame. And then afterwards, it generates the PWMs and it controls the switching such that we get the correct currents and power delivered to our motor to allow it to spin at the speed we want. In terms of the connections, I'll show you in the hardware video, but it's quite simple. We just use two standard DB37 connections to send the analog measurements from the simulator to the OP8666. And then we have another DB37 cable to send the digital gating signals from the OP8666 to the simulator. And all these screenshots, by the way, are from dashboards. So you will see that in the actual video itself, these dials, these displays, they will switch and they will alter depending on like what the actual measurements are. So on the little displays on the right-hand side, when they're running, they will show you the proper duty cycle of your PWMs. Okay, so the way it works is first, as I said, there's an initial charging mode in which the OBC is active, or the onboard charger. So that LLC topology is switching. That is what is doing the work right now. And the way we enable charging is through a switch inside our dashboards. So when that switch is 1, the battery will begin charging up. And that state of charge should be greater than 80% before we activate the motor. And while it's charging, you can see the input voltage to the LLC, and you can also see the effect of the boost PFC, and then the subsequent LLC circuit with the voltage readings there. And so this is just all to charge up our battery. But yeah, just a little bit more about the topology. The first, we're supplying an AC grid input. So it's a single phase AC input. You can kind of imagine it as the input from your house, like just plugging it into your garage electric panel. And then that single phase input is charging our battery. After our battery is sufficiently charged, we then we give the speed command to run our motor. So in this situation, we've charged up our battery and we're ready to go out and drive somewhere, go to a restaurant, go on a road trip, something like that. We're ready to go. So now we are driving our car. We're going and we have, let's just say we were driving at a certain speed. We give that speed command, and then from there, the OP8666 now shifts to controlling for the inverters with the motor. It's trying to fire the switches of the motor such that it gets the right amount of power delivery and right amount of current delivery, to get the right speed that we need. After we do that, we can play around with the speed, and we can play around with the torque as well, just to see the effects it will have on our currents. That's about it for the overall theory of the demo. I'm now just going to show the video to show off what exactly is going on inside this setup. And skip. And okay. Let me just pause. I just need to check one thing. Okay. Let me now maximize this. Okay. Okay, so this is our OP8666 on the top of the OP4512, and then we have the OP4512. So even, by the way, our lowest, our entry-level simulators are capable of using eHSGEN5 and simulating these very complex, very difficult to model dynamics. So on the top, just for reference, that USB cable that you see on the left-hand side of the OP8666, it's connected to my host computer. So the way it works is I code up and I develop my models for my control inside Simulink, and then using the Texas Instruments Code Composer Studio, I'm able to flash this model onto the OP8666, so it executes the control that I've modeled inside Simulink. So we're doing actually 2 levels of Simulink, where we're doing one to develop the control for the OP8666, and then we're doing another to model our real EV. So yeah, that's what's going on there. There are the connections for the DV37 are at the rear of the unit. And so if we go a little bit faster in the video, just skip in a little bit forward. A little bit forward. Okay, here is the rear. Okay. Sorry, 1 second. I just want that one shot. Okay. So as you can see, it is just using the standard DV37 connectors. There's nothing special here. There's no special cabling. The cables you would get with a regular OP4512 could be used, and we just plug from the OP866 to the OP4512. Once again, just to reiterate, we're sending measurements from the simulator, from the analog channels, and then those are being received by the OP866. The OP866 takes those measurements, it performs its control, it generates the PWMs it needs, and then it sends those via the digital out to the digital in of the OP4512. So moving along. And yep, so here is the dashboards demo. So this is just the main screen. The real start of the demo happens in the next dashboard. And we go. Oh, and just to provide clarity, this is a narrated video. I narrated this video at the NEAT office. So that's why there's a lot of like empty silence. It's actually because we've just muted it and I'm explaining it to you right now. When you watch this video by yourself, you will hear me talking there. It won't just be a blank screen for a minute. So moving forward, here is the main screen of interest. So this is how we start our demo. Initially, our battery will not be sufficiently charged. It'll be at roughly 75 or 77%. So I want to go out. I want to go to a restaurant with my friends. And so I'm going to start charging up my EV by enabling the charge mode. And so that's done by this little dial on the right-hand side, this little switch. On the left-hand side, by the way, are the torque and speed. Those dials are repeated also in other screens. Don't worry about it too much right now. Just note that I want to first charge up my battery, and I will do so by switching it from state 0 to state 1. And that's done at this moment. And so now my battery is charging. So you can see slowly you can see slowly that the voltage level is rising. And once it has risen to a sufficiently high level, we can then begin using our motor and our EV. So during this charging state, this is what's going on. The onboard charger is active. It is doing its work. It is taking that single phase AC grid input and it's transforming it into the appropriate DC level for our battery. So you can play around with various settings here. You can change the switching frequency of the LLC. You can change the duty cycle. You can also change various settings for the boost power factor converter. Once again, the battery is represented as just like a resistor, just a load that we are providing. You can have more complex modeling for your battery, but just for a simple demonstration, we went forward with this. And you can also, by the way, adjust your AC grid input, because I know not everywhere has 60 hertz frequency. I know some places, like Japan, have some 50 hertz areas as well. So you can adjust what your input is as well. So yeah, the battery is charging right now, and it's doing its work. Eventually, the battery will be sufficiently charged that we can begin activating the motor. So right now, our battery is good to go. It's got enough charge in it. I feel safe to go out now. So I disabled the charging, and then now I execute the speed command. So the torque right now is 2. You can adjust the torque depending on what type of, like just on the specifications of your actual EV and what it may be. So what I will do now is I will increase the speed. And so once I increase the speed, you can immediately see my battery starts discharging slowly, which makes sense. I'm using the battery to power my motor. So the battery begins discharging. Now, then we go to the motor screen. And so here we can see the currents delivered to the motor. We can see the torque. We can see the speed command and the speed reference, and just the overall performance of our circuit. And you can see that on the left-hand side as well, that's the VDC of our battery. And you can see it's also gradually decreasing, but not too rapidly. And so we can play around with the speed, we can play around with the torque, and we will get different results. So when you increase the torque, just in general, when you increase the torque, you tend to get more, you require more inertia, and the currents will tend to be more solid. Or if you have a lower torque, the currents will tend to fluctuate a little bit more, but that's just a property like the inertia of the machine. If you remember your machine theory, the torque's important for that. So here, by the way, is the last screen showing off the control. So on the left-hand side, you have all the inputs. You have the speed command, you have the speed reference, you have the speed reference, you have the speed measurement, you have the currents, and then you also have the angle of the motor. And so using these, it transforms, as I said, just to repeat myself, it transforms these using current DQ control into the DQ frame. After it transforms those into the DQ frame, it transforms it into the ABC frame. And then it gives that to our PWM generation. The PWM generation then creates the appropriate switching signals to control our inverter switches. And then afterwards, you get the magic of the motor spinning at the speed you want. Now, during this entire time, the OP8666 is running and doing its control. So it's a really just if you think about it, this is once you have your model set up, like you have your correct EV, you have your correct battery, everything, once that's set up, you can then really start iteratively improving your controller because the model's ready. You can go, it's ready to simulate. Now you can just tweak the controller settings and see how the behavior changes with your new firmware, with your new settings. It's a really effective platform to quickly and iteratively test your new controller and your new applications. But yeah, that's about it for the demo. It's a very quick one, and it's just a further step. It's another step forward, showing how we can do increasingly complicated and increasingly new applications and technologies with OPAL-RT. Thank you for your time.